Okay, so we're actually in like unit like 2B. It's like this, just the second part of unit 2 here. And we're doing polynomial functions. So, polynomial functions can be written in the form, oh, that's the wrong, yellow. Can be written in this form. Now, that looks super confusing. Let's kind of maybe just talk about what that's what that is saying. It just means something like this. If we had f of x is equal to, and you guys have seen these before, let's say it's like 3x to the 3 plus 4x squared minus 3x plus 2. Right? Like that's the kind of thing we're talking about. That's a polynomial. And it really follows this format where you've got, coefficients out front that are whole numbers or integers. And you've got just powers that are whole numbers. So power of 3, power... Actually, I shouldn't have said coefficients can be anything. They could be square roots or rationals or fractions or anything like that. But these exponents they can't be fractions. They can't be negative exponents. They're just going to be like whole numbers. Okay? So that'll be our definition for them. So you guys have done this last year too. Well, let's just look at this too. So this is saying over here, well, x to the n, right? And then x to the n minus 1. That just means we're going to write it this way where it's like 3, and then 3 minus 1 would be 2. And the next one would be n minus 2 would be 1, right? So that's a fancy way of just saying that it goes down every time. We write it with the highest exponent, and then we work our way down from there. Okay? And then the bottom number here is just like the first coefficient, and then the second coefficient, third coefficient. So, yeah. All right. So now, the numbers out front are called coefficients. So the number, like the actual values out front of our terms, are what we're multiplying the variable by. And the front coefficient, the one that's with the highest exponent, is going to be called our leading coefficient. Okay, so just careful because this would still be the leading coefficient if it was like 4x squared plus 3x to the 4 plus 5. What would our leading coefficient be there? The 3. Oh, sorry, it looked like a 5, yeah. That'd be 3. So, because you could rearrange this, right? I could put this one out front and then it would be leading, right? But it's going to be the highest exponent is what that one's with. And then your constant term is the one that doesn't have a variable attached to it, right? It's always 5. It's not going to change. It's not going to be multiplied by some other variable there. Okay? And then the value of n in the highest value of n in our expression is going to be considered the degree of the polynomial. So we would say this is a degree 3 polynomial. If we had 4x to the power of 10 plus 5x minus 4, that would be a degree 10 polynomial. Okay? That's got to be the highest one. Now, they have certain names, especially for like the lower ones, for the lower numbers. So we've done these, right? Math 10C, it was all about lines. 20-1, it was all about parabolas, like our quadratic polynomials. So you guys have seen those. The one that you won't have seen that much of is cubic. And that's just going to be a degree 3 polynomial. Okay? But they can keep going higher. So if it goes up to 4, then it's going to be a quartic polynomial. And if it's degree 5, it's a quintic polynomial. But typically we don't even use those words. After like 3, we just kind of say degree 4, degree 5, degree 6 polynomial. Okay. And then you guys have seen this before too. If you have one term, so if it was like 3x squared, that would just be considered a monomial. If we had like 3x squared minus 4, that would be a binomial. There's 2 terms there, right? 1 term, 2 terms. If I had 3x squared minus 4x plus 2, that would be a trinomial. Okay. All right. So for the following functions, state the degree, leading coefficient, and constant term. So just for the sake of time here, because I think you guys will be fine with this, let's just kind of like talk about it here. So the degree of this polynomial, what would the degree of this polynomial be? 3. Great. The leading coefficient. What would the leading coefficient be on this polynomial? 1. There really is a hidden 1 sitting out front of that thing. And then the constant term? Yeah, -6. Yeah. It'd be -6 because really it's like plus -6 technically, right? So, yeah. All right, next one. What would the degree of this polynomial be? 4, right? It's the highest one, even though it's not in the right order there. What is the leading coefficient of this polynomial? Yeah, -5, because that's the leading in front of the highest degree. And then what's our constant term? 7. Yeah, +7. Yeah, cool. Okay, so for the following examples, determine the degree, leading coefficient, and constant term first without expanding, and then verify the answers by expanding and simplifying. So this is, we're going to do the same thing, but now we just want to be able to start to do these things looking at them while they're factored, right? So while they're like in those, they're separated into those factors there. So if I wanted to figure out, let's say, our degree of this polynomial, right? If you can imagine, just imagine yourself if you had to solve this, right? We'd have to rewrite this one as 3x minus 1 times 3x minus 1. We'd expand all of that, and then we'd expand all of it into that one. It's going to get messy, right? It's going to get long. But can anyone see what it's going to be as far as x to the power of something in the end for our biggest exponent? All right, so some people got there. Yeah, it's going to be 4, right? Because you can imagine here in the end, no matter what happens, I've got like x squared, right? Can you imagine when we wrote that part out that would be like 3x minus 1 times 3x minus 1? If I just ignore the numbers completely there, I know at some point I'm going to go 3x times 3x to get 3x squared, right? So this is going to come out as like x squared for that part. So you can think about it like that's going to be x squared. I'm going to write this down. Degree. So that'd be like x squared. This part is going to be, well, I'm going to have to multiply that now by this at some point. So that's going to be another x squared. So that's all going to come out to x to the 4. Okay? Leading coefficient. So the leading coefficient. Okay. Anybody know how we'd find that one? Yeah.
Wouldn't you just multiply all the highest value terms along with multiplying them by 2?
Yeah. I think that made sense. Yeah. Yeah, because really just picture what's going to happen here, right? Is that at some point we're going to have to go this 2 times that 3 squared, right? After we did that. So you can say, okay, it's got to be that 2 times that 3 squared at some point. And then the next one we expand it out again, that's all going to have to be multiplied by that 5 at some point, right? For that coefficient. So times 5. So that ends up being 90. So I can tell just from looking at it in this form that the leading coefficient there has to be 90 in the end without knowing anything else. All right, the constant term. Okay, so constant term here. How do we do this one? Yeah.
Would it be the 2 times the -1 and then times 1?
Yep. Yeah, perfect. Yeah, so at some point here, we're going to have to go 2 times this -1, but then times that -1 again, right? If we're doing like the squared part of it. So you can think about it as like 2 times -1 squared at some point there. And then that's all going to have to be multiplied again by 1. Okay, so that would come out to 2. This is going to be a helpful skill for some of you guys' questions because you don't want to have to expand it all out, right? I'm not even going to do that just for the sake of time because we've done like a bunch of that. How are you guys feeling? I'll set it up so that we could. I want to remind you guys how we would set this one up. So if we were going to expand this all out, we would write it out again as 2. And then instead of 3x minus 1, how should I write that?
3x minus 1 times 3x minus 1.
Right, 3x minus 1 times 3x minus 1. And then times that other part. So 5x squared minus x plus 1. right? The mistake that a lot of people would do on that first one is they would go 3x squared and then -1 squared. That's going to get you the wrong answer there, right? We got to write it out again because we got to use FOIL. Okay, and then we just do the whole process here. You'd have to expand the 2 into that one. And I'll stop after this one, but we'll go, okay, this would end up being 6x minus 1, and then I put my brackets there, and then I'd write it all down again. So 5x squared minus x plus 1. And then the next thing I'd have to do, oh, 2, yeah, thank you. And then the next part there, I'd have to FOIL that one in. So I'd go that one times that one times that one, and that one times that one. I'd have to figure all that out, put it in brackets, and then multiply by 5x squared minus x plus 1, and expand all that out again. You guys might have to do these types of questions, but we did a ton of this like in past years, right, too. So yeah, I'll move on just for the sake of time there. So let's skip this one. So it says, what does not qualify as a polynomial? Okay, so these are going to be kind of key for the type of question when it's saying which of the below are an example of a polynomial. So we can't have roots of variables. So in this case, this is like the square root of 5 times the square root of x to the 3. Right? They'd be the same thing. And we can't have square roots of variables in there. Because really, that would be like a fractional exponent. That would be the same thing as like x to the power of 3 over 2. You guys remember how the exponent there is the top part of our fraction, and the root is the bottom part of our fraction? So it'd be the same thing there. You can't have absolute values of variables. We can't have negative or fractional exponents for really the same reason as the square root up there. And the negative exponent, what that would do, right? That would be the same thing as this one. You can't have variables in the denominator because x to the -2, that's really the same thing as 1 over x to the 2, right? That is like having a variable in the denominator. So we can't have that. And then any non-real coefficients. So this just doesn't exist. The square root of 4, even as a coefficient, is a number that doesn't exist. You can't take the square root of a negative, so it can't be. So looking at this one, let's say, are these polynomials? And I can see a fractional exponent, so no. So for B, what would be the problem here? Yeah.
So the -2 exponent.
Yeah, -2 exponents, so no. All right. C, what about this one?
The square root isn't including the variable, right?
Nice, yeah, exactly. So it's just, it doesn't go right over top of the variable there, right? Like it's not over top of the x squared. So we're still good. Actually, that one still would have been good too, but we're still good either way. So coefficient is just square root of that, which is fine. So not root of variable. So root not on variable. So yes. Therefore, yes. Okay. What about this one?
No.
Yeah, no. Next one here. So what about this? Square root of 3x to the 4.
Would we be able to take the x to the 4 out, or do we have to leave it in?
Good question. Yes. So you could rewrite this part here as, well, this would be the same thing as, well, the square root of x to the 4 is what?
X to the 2.
X to the 2, right? So this would be the same thing as just saying the square root of 3 times x to the 2. And now it's no longer taking the square root of it. So this one would still be okay. So yes. Okay, what about this one? It's like a rational expression like you guys have been doing in the last lesson.
So if it's an even exponent, you can take it out. You can take it out.
Yeah, yeah, good call, yeah.
So why isn't the rule of roots of odd?
Okay, so what about f? Yes or no for a polynomial? No, right? It's in the bottom. It's in the denominator, so no. Okay, what about this one for g?
Yes.
You can't do it because you just can't take the square root of a negative number, right? Even for it would be fine for the coefficient, but we can't have that square root. And then no because of the absolute value on that one.
Wow.
All right, so characteristics of polynomial functions. So, to kind of get a grip on these, just one sec. If we have a degree 0 polynomial, well, first let's think about what that even would look like. A degree 0 would be like y is equal to 3x to the 0, or something like that, right? What would that be? 3x to the 0. Can I write that different?
3 times 1.
Yeah, anything to the power of 0 is just 1, right? So that's why degree 0 works here. This is really just a constant term. This is like saying y is equal to 3, just some number, right? And what do graphs that are just some number look like? Like if we had y is equal to 3, well, that's just this, right? It's just a straight horizontal line. Okay, so that, yeah, I think you guys would be fine with those ones, right? Where it'd just be a straight line. Math 10C, we did a ton of these, right? This is that classic y is equal to mx plus b graph with a degree of 1 there. And that's just a straight line going up, right? That's that slope. So rise over run would be your m value, and then your b value would be your y-intercept there. Okay, and then 20-2, we started doing quadratic functions, and they were that parabola, right? Do you remember what the rule was when we did these ones? So if I gave like this example here, where it's f of x is equal to 2x squared minus 3, then how do I know whether the thing opens up or opens down just based on looking at the function there?
The leading coefficient is positive and negative.
Yeah, and do you remember like the rule that smiley face or frowny face there, right? So if it's positive, then he's being positive, right? So smiley face there. So we've got a smiley face going on here. Okay. If this was negative, then it would be a frowny face. And it would be opening downward like that, right? Okay, so that's for our quadratic functions there. And then our y-intercept would be the number hanging off the end, right? Okay. Okay, now moving on to the next ones here, though. Degree 3 is always going to look something like this, where it's going to go like from the bottom left, right, from like quadrant 3 up to quadrant 1, like that's always going to be the case, quadrant 3 to quadrant 1. And it's going to extend to infinity all the way to the left. Like you can imagine this arrow is going down that way, but really it's going infinitely far to the left. This thing never stops. And same with this one. This is going infinitely far to the right, and infinitely far up, and infinitely far down. So our domain of this one is going to be any real numbers for domain and for the range. Okay? And they're all going to do this funny squiggly thing. They might look different based on what the graph is. We're going to figure out like how to find those squiggly things and what's happening there. In calculus 2, we're going to find like areas of local maximum and areas of local minimum and all that kind of stuff. But for now, we just need to kind of know that they do a squiggly, right? They're going to squiggle up like that. And generally, these are the same type of thing as degree 1, right? Odd degrees are all going to have this in common, that if the number out front, so like on this one here, this is a positive value out front, it's like positive 1. Do you remember if you had a positive slope, well, that would just be going from the bottom left and up, right? Like positive slope looks like that. Same thing here. Generally, we got the same thing. It's going to be going up. Even though it has that squiggle in the middle, that's going to be the general shape going on. So if there was a negative out front of this, if I just change this to negative x cubed, yada yada, what's going to change there is it's just going to start up here and end down here, right? Just like a negative slope would on a degree 1. So that one would do something like it would go down and then up and then down again. Yeah, you guys good with that? Because if you got that down, that's pretty much it. As they go higher, they start to kind of follow a pattern. So degree 4 is actually just a lot like our degree 2. Do you guys kind of see how they're similar? This one started up high, ended up high, started up high, ended up high. We can still use our like happy face, frowny face thing to figure these ones out. So If it's positive out front, it's going to be a happy face, but we've just kind of got like a weird smirk going on now. It's a smile, but it's just kind of like a, I don't know, a funny looking face. Okay, and then same with the if this was negative. So if I put a negative out front of this one, then it would be similar to what we were saying before, but it would just go up, go down, squiggle, and do something like that. Okay, and then you can see degree 5, really similar to degree 3. There's just more squiggles in between, right? It just goes up and down and then up again. And yeah, so that's the idea. But same kind of general pattern. If it's an odd degree, it's going to go up this way. Or sorry, if it's positive with an odd degree, it's going to go up that way. And then if it was negative, it would go like down like that. All right, good. Okay, I kind of explained all of this stuff in that one there. So here, I'm going to pause it for a sec. Like this, where it's going to do like a happy face type of a thing. Odd graphs are going to do something like that with a squiggly. Negative even graphs would do something like that with a squiggly. And then odd, negative odd graphs would do that. And when I say even and odd, I'm talking about the degree of the polynomial, right? Yeah. All right. So every time the graph crosses the x-axis, that's counted as a 0. Now, let's like just talk about that for a second, what we mean. So if I had, let's say, a function, and it was y is equal to x minus 5, x plus 2, and then I said solve for this when y is equal to 0, what would your answer be? X minus 5, x plus 2, x would be equal to what? Yeah. Yeah, 5 or negative 2, right? So 5 or negative 2. And we've been calling those the zeros. We're just doing the same thing, right? That's what this is kind of saying here. Our zeros here, right? This is like our x or our x axis would be at 5 and negative 2. So every time the graph crosses the lines, right? So in this case, that was a graph looking like this. It's going to be the same for our higher degree polynomials. Wherever they cross the x-axis, that's going to be our zeros. Okay? So there's different ways that this can happen sometimes, though, with our graphs above. So sometimes there'll be a straight through. So that might look like this, where they'll go up and then straight through again. But do you guys remember from quadratics last year, do you guys remember what the word discriminant meant? The discriminant of the equation with our quadratic equation? Yeah?
Wasn't it the, in the quadratic formula, the negative d squared?
Right. You ended up taking like the square root of the negative when you used the quadratic equation, or quadratic formula there. That meant that it had no real solutions. So that could be the case too. Like it could also just not pass through at all, right? You might have no zeros on that thing. Might pass through below. Or there was a situation when we did the quadratic equation too, where you only ended up with one solution. And that was the same as just touching the x-axis. And then you can also have like a point of inflection where it would go up, like it's like heading this way, and then turns and goes that way. So inflection, because it's like going, it's curving one way, and then right when it passes through there, it starts going the other way. It's like inflecting on itself. That again, that's another 30 or calculus one that we do a lot with. All right, so let's do this one quickly. Let's just match these graphs up. So it says the type of function, yada. So whether it's even or odd degree, the end behavior of the graph, the number of possible x-intercepts. Okay, so looking at the negative out front on this guy, what do we know about our graph? Yeah, it's going to be a frowny face. And I'm doing the frowny face, happy face thing because we have an even exponent there. Yeah, so it's going to be like a frowny face. It's opening down. So which of these graphs, even just from that, do we think it is? Yeah, it's got to be D, right? That's the only one that would be, right? It's like that's our frowny face with a funny smile there. Okay, but we could also see that from this graph, we have a degree 4 polynomial, which means that we have a maximum of 4 x-intercepts, right? If we have a degree 4, that means that it could cross the x-axis 1, 2, 3, 4 times. It might not have, right? Because this thing might have went up here, came down like that, up and then down. Like that could have been the case, but we have a maximum of 4 x-intercepts there. Okay, so max 4 zeros. Okay, and then the y-intercept. What's our y-intercept on this one? -4, right? So that'd be your y-intercept. And that could be right there, -4. All right, next one. Let's look at this. So we've got an odd degree. So I'm expecting this one to be like not a happy face or frowny face. It's going to be like squiggling up or squiggling down, right? It's positive. So which quadrant is it going to come from and go to? It's going to start in quadrant 3 and end in quadrant 1, right? It's going to be generally like up like this. Okay, and then cross at 3. It has a maximum of 3 x-intercepts or 3 zeros. So which one are we dealing with? Yeah, it's got to be A, right? Oh, sorry, in the last one we could have put D for that one. And then this one was A, we said? All right, looking over here, degree 5. Okay, so again, it's not going to be a happy face, smiley face thing. It's going to be like sloped. And it's going to be sloping down, right? So the only one that makes sense here is going to be this one. It starts up in quadrant 2 and ends in quadrant 4. Okay. And then the last one here. So we've got a +4. It's going to be opening up, right? So the only one that could be is this one. And it has 4 zeros, and it does cross at -12. All right. Okay, so a bank vault is built in the shape of a rectangular prism. Its volume V is related to the width W in meters of the vault doorway by the function yada. So here's our function, okay? Now it says, what's the volume in cubic meters of the vault if the door is 1 meter wide? Okay, so all we got to do there is plug it in to the function. So this would be V of 1 is equal to 1 to the power of 3 plus 13 times 1 squared plus 54 times 1 plus 72. And that's equal to 140 meters cubed. Okay, so now it says what's the least volume of the vault? And what is the width of the door for this volume? Why is this situation not realistic? So remember, the width is the width of the door in this vault, right? So as the door gets bigger, the vault gets bigger too. So if we graph this, what we're going to see is it would go like this. It would go down here, it would go down here, and then up again. And our y-intercept, like right where it starts, well, even without graphing, do you guys know where that would cross the y-axis? Yeah, 72, right? So we know that it starts at 72, right? So that point there is the point 0, 72. Okay? Now, this is like our real world situation, right? Do any of the numbers on this side of the y-axis, right, the negative x values, do any of those make any sense? Right, that's saying like a negative door value. So if your door is like this wide, what that is saying is that you've actually gotten like smaller, 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 smaller. And now we're into like the negative territory. We're like going the other way, right? None of that really makes any sense as far as like an application question. So that's not allowed like in our domain, right? That we would write that as x has to be greater than or equal to 0 in this case, right? Because the door could be 0, I guess. But okay, so we're going to start from here. Now, why? So here, let's actually say that the domain of this would be w has to be greater than or equal to 0, and the range. What would the range be?
Y has to be equal to or greater than 72.
Yeah, or v has to be greater than or equal to 72. Okay, so it has to start here, right? That's as low as it can go. Okay, and then why doesn't this make sense? Yeah.
I mean, you can't really have vol without a door. You can't.
Right. You can't have a vol without a door, right? Because this is saying that it would start at 72, but that would mean that the door actually had no width, right? There was no width at all on that door, so that's not realistic. You can't even get into that thing. Yeah, okay. Okay, last question. So this one says p of x is equal to negative 3x squared plus ax plus 8. And it says determine the value of a. So it wants to know what is the coefficient on this, given that p of 1 is equal to negative 9. Any ideas on this one, how we could solve for this?
X in F1 and then solve for A.
Yep, and then, yeah, exactly. So remember what we're looking at here, right? When we've got p of 1 is equal to negative 9, where do I know a point is on this graph? Right, when x is 1, y is negative 9, right? So that's a point on the graph. And that's an x value, and that's a y value. And I got to solve for that a, right? That's a number I can solve for. So if I can just replace, this y and these x's with these numbers, then I'm left with all numbers and then just a to solve for, right? So it'll just be straight algebra at that point. So we'll plug that in. So instead of p of x, that's like our y value, right? We'll type in negative 9, or write in negative 9 is equal to negative 3 times 1 squared plus a times 1 plus 8. Okay, so that's going to be negative 9 is equal to, this is just negative 3, right, because 1 squared is just 1, plus a plus 8. Okay, so negative 9 is equal to negative 3 plus 8 is 5 plus a, and then minus 5 minus 5, so we get negative 14 is equal to a.